transformers for human action recognition.
Assalamualaikum. I'm Nija Asif, and today I'll be presenting our paper titled Dynamic Temporal Modeling using Cascaded Deep Networks and Encoded Transformers for Human Action Recognition. This work was done in collaboration with Hasib Amjad, Dr. Umar Shahbaz Khan, and Dr. Hassan Elahi from the Department of Mechatronics Engineering, National University of Sciences and Technology, Islamabad. In this presentation, I'll walk you through the key aspects of our work, from the motivation and approach to the results and conclusions. So let's get started. It's 3 a.m. and an elderly person collapses at home, while no one is around to help. In a nearby city, a security camera captures an incident in real time, but fails to distinguish whether it's a harmless interaction or a potential emergency. These scenarios highlight a simple truth. Machines can see, but they struggle to understand. Now, imagine a world where technology not only sees, but accurately interprets our actions, detecting a fall before it turns button, recognizing suspicious activity to ensure public safety, and even improving interactions in classrooms or workplaces. This transformative shift is at the heart of human action recognition, where machines bridge the gap between observation and understanding, an idea that's no longer science fiction but the focus of our research. But what is human action recognition? Essentially, HAR bridges the gap by helping machines better understand and interpret human behavior, making it crucial for a wide range of intelligent systems. HAR identifies activities like walking, sitting, running, and much more from short video recordings. It's a major area in computer vision with applications in fields like robotics, healthcare, surveillance, sports, and human robotic interactions. Now that we understand HAR and its significance, let's discuss why it's still a major area of research. While a lot of progress has been made, HAR models face key challenges that limit their real-world applications. For instance, variations in actions like different reading styles make it difficult to generalize. Additionally, environmental factors such as lighting, camera angles, and oscillations, as well as complex scenarios like overlapping actions in crowds, add to the difficulty. Finally, balancing accuracy and computational efficiency remains a challenge, especially for real-time use. Addressing these limitations is crucial to fully harness the potential of HAR. To tackle the challenges in human action recognition, various approaches have been explored in recent research. For instance, one paper used histogram-oriented gradients with support vector machine-based to detect falls, focusing on motion features for elderly care. Another approach combined Gaussian mixture models with Kalman filters, leveraging probabilistic modeling and motion smoothing to empower action recognition. Deep learning methods have also been widely adopted. A study proposed a 2D spatial temporal motion network with spatial attention to capture both motion and focus on critical regions. Another combined with CNNs with LSTMs, where CNNs extract spatial features and LSTMs handle sequential data, making it ideal for sensor-based recognition. Innovative methods like optical flow GRU have also emerged, using optical flow to capture motion efficiently. Finally, a two-stream neural network approach combined with spatial and temporal information, improving recognition of complex actions. These works showcase diverse techniques from traditional methods to advanced deep learning approaches, each addressing specific aspects like motion, special features, efficiency, and good accuracies. However, the need for robust generalizable model for real-world application still remains a key focus of ongoing research. Building on the literature review we have done so far, it's important to recognize the key challenges faced by traditional methods. These methods struggle with fine-grained motion, making it difficult to distinguish subtle actions like walking versus jogging. They also fail to effectively model complex temporal dependencies and dynamic interactions, which are critical for recognizing sequences of human actions or interactions with objects. Additionally, scalability is another challenge, as these methods often require extensive turning of new environment or datasets. They tend to generalize poorly across diverse datasets and suffer from high computational costs, making a real-time or resource-constrained application impractical. These limitations highlight the need for more robust, scalable, efficient solution to advance HAR for real-world use. To overcome the limitations of traditional methods, our proposed method focuses on dynamic temporal modeling. This approach captures spatial, short-term, long-term, and global dependencies, enabling it to effectively handle both fine-grained motions and complex temporal patterns, while balancing accuracy and computational efficiency. We employ a cascaded architecture that integrates CNNs, GRUs, LSTMs, and transformers, leveraging the strengths of each. These components are combined with efficient NetD0 for efficient and robust feature extraction. Ensuring scalability and adaptability, this design directly addresses the challenges of traditional methods, paving the way for improved performance in real-world scenarios. These are the key highlights of our research. We have a hybrid architecture, enhanced temporal learning, improved spatial-temporal representation, global context integration with scalability and flexibility. Okay, now that we have to train our model, we considered several datasets. The options included UCF 101, UCF Sports, and KTH. However, we chose the UCF 50 dataset because it strikes a balance between complexity and size. It provides 50 diverse section classes and 6618 video clips, making it more manageable than UCF 101 while still offering significant variety and realistic conditions like varying viewpoints, oscillations, and scales. For pre-processing, we resized frames to 48 by 48 pixels and processed each video into 15 frame sequences. Labels were one hard-encoded. The dataset was split into 50% for training and 25% for each, testing and validation, with 3309 videos for training and 1654 for testing and validation. Before we dive into the detail of model architecture, it is important to understand the basic areas involved in this model. First, we have CNN. CNNs are responsible for the feature extraction. Input data goes through a convolution to detect patterns, followed by pooling to reduce the dimensions. The extracted features are passed through dense network for classification, leading to the final output. Apart from this, we have used LSTMs and GRUs. The LSTM and GRUs use recurrence for sequential processing, while the transformer encoder uses self-attention for parallel processing, making it more efficient. Okay. Now here comes our model architecture. But I think if I keep reading on it and try to explain it, it's a little difficult. So let's imagine a real-world scenario. Let me walk you down. Okay, so this is the architecture. I hope I am audible till the end. Imagine you are in a scenario where you have to investigate a crime scene. There are 4 detectives. Our first detective is the CNN layer from 1612 to highlighted block till here. Then we have our second detective, which is a GRU. Third detective, LSTM, and then we have encoder, block, transformer, or 4G. Now, the moment you are present in one scene, you have to detect whatever is going in that scene. You have to extract the features of that scene. That's where the CNN comes in. They can only work in real time. Now, imagine you are in scene number 5, but you got a map in, let's say, scene number 1 to investigate the whole area. Now, you have GRUs. GRUs can only recognize the information that's just like a short-term memory, something that just happened in the previous scene. Say if you are in scene 15, it can go back to scene 14, but in a sequential manner. Next, as I mentioned before, you were given a map in scene number 1. That's where the LSTM is. LSTM are the long short-term memory. They can go back to the first scene as well, but in a sequential form. Now I think that's a little problem. I am in scene 15, I have to get something from scene 1, and I have to go back sequentially. Don't you think it's very time consuming? It is, I guess. That's where the encoder block dies. Transformers are responsible for parallel pre-processing. Parallel processing, they can extract anything from any scene of the video as per your requirement, and that's what makes it the most efficient detective of ours. After that, we have this global average pooling layer to reduce the sizes, then have normalization, and ultimately the classification. Okay, now you might be thinking why a lot of things are involved here. CNNs, LSTMs, GRUs, transformers, and On the other hand, I'm saying that I'm trying to make the model more computationally less expensive. Okay. So for that, this slide explains the rationale behind our model design. We use CNNs to extract spatial features from individual video frames, enabling us to capture the local spatial information efficiently. Next, GRUs and LSTMs are employed to capture temporal dependencies, both short-term motion patterns and long-term sequence relationships with the video. Finally, transformer encoders help capture global dependencies across the entire sequence, providing a holistic understanding of the video. Here I'll quickly explain the experimental setup. We use 100 epochs with SCD optimizer for optimization. Training efficiency was improved using a learning link scheduler with a minimum value of 1 prior to 6, and early stopping was implemented to prevent overfitting. The table shows the experimental setup. Next, here's the confusion matrix, but since it's a matrix of 50 classes, it's a little difficult to visualize, but you can see the results in the table. In this result, the model has demonstrated high precision and recall for most activities, including real-level identification, without significant errors. Some activities show slight lower performance, but overall the model retained a reasonable level of accuracy, even when misclassifications occurred. Since recall was the most crucial metric in this study, the results achieved are notable from the table for 50 classes. The macro average precision recall and F1 score were approximately 0.92 with a weighted average of 0.92 as well. The confusion matrix on the right further visualizes the strong performance across different classes. Okay, so for a peer comparison, we have added a comparison and validation slide as well. This section highlights the superior performance of the current approach, achieving 92% accuracy, outperforming previous methods like distance transform, con-LSTM, 3D CNN, con-LSTM. The accuracy and loss graphs show rapid convergence with stable performance, demonstrating both effectiveness and computational efficiency. While some studies report slightly higher results, they often use different datasets or experimental setups. Our method not only ensures robust generalization on challenging 50-class dataset, but also achieves this optimized training strategies, including learning aid, scheduling, and early stopping, which enhance efficiency and reliability for real-world applications. We have achieved 92% accuracy on UCF50 dataset, with recall prioritized to ensure reliable detection of complex actions despite oscillations, misclassifications, and future work involves improvements including integration of multimodal data like sensors, exploring temporal attention mechanisms, and expanding to larger diverse datasets. Additionally, deploying a model for real-time application and incorporating self-supervised learning while enhancing robustness and scalability. Thank you. And